Well, first of all, thank you so much for inviting me. Apologies, I can't join in person this semester I'm teaching, so it makes me really hard to travel and make a quick turnaround in a few days. But I really appreciate the opportunity to speaking to all of you regarding some of the recent research work and some of the thought process. And I also want to clarify that today's talk, I'm not necessarily presenting a ready solution per se, and a lot of it is really related to my thoughts. Would love to have more discussion um, towards the end of the talk, rather than me presenting a work or a formula or some of the results. I'd rather to maybe open the flow for more discussions at the end, and particularly if you see anything that potentially could be extended and related to your work, feel free to throw like your thoughts and or maybe challenge me. I'm happy to have a more interactive discussion as we go. So today I will be primarily talking about two keywords. Really, it's the one is the large scale, some of the data, multi-source, high granular data, and the other part is the keywords is the large scale networks. I'm very passionate about the building some sort of network, leveraging data. This will be really the scope of today's talk. Oftentimes I get thrown the questions that saying, especially work with a lot of the computer scientists and engineers and environmental engineers, and also people coming from very, very different background, that they always ask me, Sean, now we have a lot of information about the networks, right? If you look at Google Maps, we have a very good understanding of what part of the road is congested at any time of day. We know the transit arrival time, parking occupancy into some sort of categorization occupancy rate. We know a lot of information about the city. And why do we need you, and why do you need to do network modeling anymore? Whether the sensor, the ubiquitous sensing, be able to solve everything. It's oftentimes it's something I sleep on too, right? So with all the data technology, AI, machine learning, sensing, whatever the buzzword is, what can we do, or what is really necessary, and how are we really doing the work that is almost necessary to bring our work to solve some of the real world problems. And then I'm always thinking about there's actually two pieces missing. It's all related to the ability to forecast or to predict. The two time scales. One is a relatively short time scale, next 5-10 minutes. Can we predict what the traffic flow might look like in the next 5, 10, 30 minutes, which is not something in the Google Map. It's not necessarily a trivial task to forecast, especially under these big events and adverse weather conditions, how things might turn out to be in the next 30 minutes. Therefore, we can take some proactive actions. Again, this is not something a private sector or just necessary sensing company will be able to achieve. The other is we talking about more kind of longer term time scale. We're looking at more planning or operational planning purposes. Say if we close the road tomorrow, if we were to do something, if we were to charge congestion pricing $10, $9 toll, and right now on the bridges all going to the New York City, how things might turn out to be, right? So we want to have this ability to foresee what things might be like, under these what if scenarios. So, essentially what really interested me most is leveraging all these data and the ubiquitous sensing technologies and whatever the technologies, be able to solve the questions for these what if, right? What if we have Uber, Lyft picking up passengers at the rate of $5 per mile? What if these roads all these road segments has to be retrofit? How do we schedule? What's the social impact? What if we change the land use, or we turn some downtown from office spaces to residential zones? What if we change the bus schedules, and if we route bus a different way? But anyway, so the point being the ability to make some sort of decision, the ability to forecast what things might look like under the what if scenarios is really what the kind of scope of the topic, and I think it's really critical. And now I think about can we if there's a mysterious and a magic way, right? So we could come up with some sort of function. It's a very big function called G function, and you somehow can throw it to say, hey, now this big G function, here's the demand. Whatever way, I'll discuss a little bit how we can present the demand in whichever way we like, and everyone has different perspectives. But let's say somehow we can throw in, hey, this is how many people spatially, temporally, and the people wants to use it. Potentially people live and people wants to take different actions and go to different places. And there's also, sorry, this is a demand, right? There's also supply side. Hey, this is how things are being laid out geographically. Two-lane highway, you have 5 bus routes and 1 metro route. The schedule is 5 minutes highway. Everything somehow magically can throw into this G big function, and then somehow the G big function can give us some sort of performance of the system. That would be magic, right? And then we really want to, I mean, believe it or not, the engineers and traffic engineers and planners and urban planners, and we are doing this actually, believe it or not, in the past decades of work. The specific perspective I'm going to discuss more today uh, is this perspective a dynamic, large-scale network modeling. And traditionally, the way we think about the problem is that imagine that we have a very large-scale data set. It's let's say in entire city of Chicago, we might have 10,000 locations that give us counts, hourly counts. And we might also have index data give us every single road segment. There's a speed measurement every 5 minutes, right? So this is what I call the conventional way is that let's say we have collected data for a whole year, entire year, every Wednesday, entire morning peak, 8 a.m. to 11 a.m., for example. And then we try to take the average Wednesday, and then we try to use our model to represent a very typical representative Wednesday AM peak. The way we do things is actually, even though we have multi-day, source data, and this is essentially just a one single, it's a high dimensional, but it's one single set of data points. And we try to say, now this is data point, this one typical representative day of multi-dimensions, and throw it into the model, try to calibrate it, and let's see how, right? So really this is one single data point, but even with one single set of data points, it's still very extremely hard to replicate that data in a high dimensional space in a very large dynamic time varying network model. The other the other extreme is we have entirely data-driven approach. So we have a few years of very every 5 minute data, speed counts, whatever, and there's a large volume of data, multi-day, multi-year, and we come up with some sort of a pure machine model or regression model or whatever classification, whatever this is. And it turns out the model can fit it pretty well because you have a whole lot of freedom and you assume some sort of relationship without necessarily knowing what the traffic flow model underneath it. And you can fit the multi-year, multi-day data pretty well. But the challenge here is that it's very hard to have the ability to forecast. You can forecast in the short term, you can forecast to a certain degree, but it's extremely hard to say now, tomorrow, we're going to charge $10 toll on the street, what things might look like. Because essentially, if you don't have any behavior model, if you don't have any domain-specific model, the data is not, hasn't really learned enough from the historical data. Even you have 10, 20 years of data, but whatever happened in the past is never going to, well, I never say never, but it's unlikely to give you any clue about what tomorrow, which you have entirely new policy or strategy, how things might look like. It's just simply the machine hasn't really learned it from the past. So it's very hard to incorporate that what if scenario. So now makes me think, is it possible that we can meet somewhere between? Again, people have been doing a lot of work. This is the buzzword and in computer science and the foundational model. But I'm not trying to throw out a buzzword here. I might just try to think, learn some of the, can we learn some ideas from these linguistic foundational models, and is that possible we can train the machine with some sort of large-scale data, day-to-day, multi-year, multi-source, high-dimensional data, while we still give the model some sort of basics, physics, behavioral model or traffic flow propagation, and because there's certain rules, physics that really governing how we're making choices, how the vehicle will flow, propagate over time and over space. And so the bottom line here is the big G function has really to see whole lot, all sorts of cities, all sorts of street, all sorts of geometry design, and different people's perspective, how people making choices. You really have to see a whole lot of variations and over demand and the supply, high dimensional space. And now all boils down to how can we come up with the best embedding of all these features. If we want to represent the demand or supply in a very precise or very inclusive way, what is the best way? I mean, in language processing, now we all know the transformer or whatever, they use a very, the itself is very, very, very hard. It's non-trivial. There's a very relatively standardized way to embed all the languages, phrases, and sentences, therefore leading to a very big success of the ChatGPT or some transformer, the deep learning models. But can we do something similar? Again, I don't have the solution yet, but I want to propose today. You will see in the next 20 minutes or so. I want to throw in some concept or some very initial work that along that line that we might be able to leverage towards that goal. Not the embedding part, but it's just the whole idea is to try to come up with very flexible generic framework where you can always represent, assuming you have very good embedding, which is of course the research gap, one of the research gaps. Assuming the embedding is correct, somehow you can throw out the demand and supply into a very kind of very generic computational graph approach, getting you end-to-end design from demand supply to the output. And once you throw in the data, and it can be any kind of data, can be any dimension, the model can run it by itself just to learn all the parameters, everything, leveraging the cutting edge machine learning computational graph and all the algorithms. Then it might help us to adapt to technologies, the data, and then we can come up with different ways of design this specific neurons in this whole computational graph approach to achieve our goal. But here are a couple of possible examples, but that's kind of the general framework of the idea of what I'm going to present today. So here is a very initial, again, example. It's not the only way to represent all the performances. Start with the performance part. Remember, G function is combines the supply and demand to the performance, right? The performance part being, let's say in a traffic engineer, we're very interested in understanding time varying link flow or path flow, because that's something we can have some control over to influence the system. And then we also want to interested to know the time varying system states, such as time, cost, emissions, whichever you want to throw into it. So through this whole performance, you do have some measure, not everything. You have spots. The sensing part is relatively sporadic. So you might have some sensors and give you some counts and speed and at certain locations. And namely, the very big dimension of that dimension space of this performance, you do have some coverage that tells you something about the performance, right? So the whole point is that can we really use, again, I'm assuming some sort of batting, but assuming the batting is acceptable at this point, we don't know yet, but let's assume this is acceptable. The one way of thinking is demand can be, that's a very traditional way of representing demand, is saying the demand, we have to cut the entire zone into TAZs, and these are the demand origin destination. Every 5 minutes is what we call a Q, small letter q, to approximate the demand. We also have some sort of network capitalized N to represent the network. Again, this is a high dimension. So the G function will really be mapping the network N, right, and the demand Q with all the theta is a bunch of different high dimensional parameters. So these parameters might be the governing how the traffic flow propagates, also might be governing how people determining how people making choices. And we know in a huge network, people have the choices of destination, parking, route, mode choices, yes or no, I'm going to make the trip choices. And there's and departure time choices, right? There are many different choices, and it gets to a little bit more complicated. But the bottom line, we try to come up with this G function from a very relatively simple case to see whether this is possible, or maybe at least we have a unified framework to work with any specific general network, specific general demand, some sort of a general supply, and it can be any set, a combination of data sets across any spatial temporal dimension, and then we can calibrate this model. And well, if we have this G function, calibrate everything like the Q, we assume that in this case, the supply side N, the capitalized N is fixed because something we know, 2 lanes, speed limit 50, it's a stop sign, and we know some information about the N that doesn't really change as much, so can significantly alleviates the complexity of the problem. But let's say the demand side Q and the theta represents some of the parameters for both demand and supply. These are unknown, right? It essentially becomes a kind of parameter tuning or learning problem. We have some measure of X, F, and C, which is link flow, path flow, system states. Can we learn about these parameters Q and theta to calibrate this G function? So next time when we want to have the ability to forecast, hypothetically things might look like, and we can change the supply or change the demand side, change the behavior governed through, categorized through all the theta parameters, then we might be able to give us a very more realistic estimation of the performance rather than completely relying on a non-physics based pure data-driven approach. So that's kind of, well, this approach is not entirely new because again, I'm just trying to revisit and categorized in a very different way. But essentially, this is what the people in the network committee, network community has been doing a whole lot in the past decades. Taking DTA, dynamic traffic assignment, as an example, the origin destination estimation process itself is some sort of a calibration process. However, the much bigger challenge is at least a few, but just to name a few. One of the biggest challenge, like I said before, is that we essentially work with a typical Wednesday AM peak 5-minute data. It's not day to day, and we have actually a whole lot of data, way more than this much higher dimension data to calibrate the model. We're not really using it. Even with one single set of data, the model itself is very, very hard, very, very challenging to fit that. We cannot necessarily replicate the network simulation just as like this is really what the quote unquote digital twin system, right? And it's we're just not very confident. There's no necessary. I mean, if we dive into the more details, and technically there's a very little approach that we can do to do that. It has to be multi-class and have different vehicle classes, different modes of transportation. And then oftentimes people think about agent-based model, but agent-based model has its own issue. But then continuous-based flow model, flow-based model also has its pros and cons. And then when people making choices, typically we, at the very large scale network level, we typically consider people only making choices between the time and cost. But there's actually a way more like safety, incident, reliability. There's a whole lot of other factors that people consider when they're making choices. These all can be parameterized. And the last question I listed here is that can we really run this for very large scale network? And then for relatively small network, and we can probably do in relatively easier way. But for a very large scale network, can we fit the data, high dimensional data, multi-day, multi-year? But can we learn from these data to truly calibrate our big network? So I'm going to skip a couple slides here, but the basic idea is that we try to revisit what we have done in the past with some tweaks, of course. So at the central level, it's really some sort of simulation model. It could be analytical, could be simulation based, but essentially it's a path flow maps to the link flow and the system performance. the self can be mesoscopic, can be microscopic. And mesoscopic is just what I use mostly because that's I think it's a very good balance between computation efficiency versus accuracy, granularity. So you can use cell transmission, link queue, there's many different choices. You also want to model different vehicle classes, car, truck, buses, and that really give us a lot of second by second vehicle traces through this whole framework. And then therefore you can come up with any metrics you like and any spatial or temporal granularity, right? So remember, this is a mapping from pass flow to link flow and system performance. Here's just example, a lot of work we did to try to build a super network and not just limited to auto network, but also build on top of it the transit, micro mobility or parking and the metro system. So we have some work on that. But wrapping that, but this is what the bottom layer, but the middle layer is I use this is probably not a very good name. I use the equilibrium solver, but essentially the idea could be disequilibrium, could be any stochastic, whichever. But this is really about determining how people making choices. So if people making these choices, and then you can throw it into the bottom layer to run all the simulation. But clearly, people making choices about the route mode, parking, departure times, and many more other choices. So this is about translating that queue to some kind of pass flow. By itself, we know this is a kind of fixed point problem. It has to route it over to the bottom flow in order to make some sort of a predictive equilibrium. So with this whole process, we can build into a lot of generalized distributed function on top of just the time and cost. We can actually build a lot of other type of waiting time, cost, fare prices, service fee, and inconvenience, perception of inconvenience and crowding. So that's all possible. And then at the very, very, very out layer, right? So if we know how Q with a theta, and then with a Q, we can determine an X, the F, and C. Now the question is that can we tune Q and theta in order to fit the data? But then, and like I said, theta can be behavior model parameters, can be supply model behaviors, supply model parameters. And then this is the out layer, but this is called the data calibration learning process. But a part of this special case is really the dynamic OD estimation. Now we simply wanted to tune Q in order to fit the data. But like I said, in practice, typically the fitting won't be very good because the large dimension and because we're not really fully utilize all the multi-source, multi-data. Here is our how we come up with a very unified generic computation graph approach to build the entire process. Like I said, three different layers. Starting from the very left, you have line up all the origin destination time varying demand and people making more choices, then going to the second left layer. Each bucket really means that it's a very complicated kind of neural network design. And then you go to the route choices and you go to loading the network and becomes the link flow. And then you can also get all the link pass flow cost, right? So then at any layer, you can have this. Here's the 5 layers, just example. You can have actually multiple. You can even look at community, let's say total whatever layer you can design in the whole entire process. And any layer at any point, you have some measurement. Could be system level, could be individual level. Here I give them some examples. We might have some historical OD. We might have some observed link flow, which at this link flow layer. We can also have some cost, probe vehicle speed at the most right layer. My point being, any layer at any point, you can somehow you have some sensing system that gives you some measurement, right? This is what we call, extending to the machine learning approach, is what we call the loss function. You can define different loss, but this is a very, very flexibility, a lot of flexibility we can build in. You can calculate this discrepancy, what your model come up with, and versus what actually the observed data is to calculate the discrepancy. So this is typically what we call the forward process in the neural network design. And then you can, from left with the initial value all the way to the right, and along this entire process, remember every single layer, you could potentially have any sensing data that gives you some calculating or any type of loss. I have more examples later on. But that loss will translate backward propagation to be amplified or be used to change your step size and gradient directions to move to change incrementally your parameters in a way to move the whole loss towards zero. Some of the loss could be irreducible, but in general, these loss can go towards being minimized. But this is again, this is relatively this is idea we learned from the neural network approach. It's just revisiting. A lot of it probably has already been done. In a very conventional way, but we try to give it more flexibility, give it more vehicle classes, different modes of transportation. We add a whole lot of it, but with this unified, very generic design, the hope is that it can really be adapted to any type of network, any type of data, and you just have to come up with the right neural design and the right loss function. But there's, of course, there's a whole lot of challenges. How do you calculate derivatives? And if we have time, we can discuss more. I will give you a couple of examples. This is the example that with the very traditional data we use. We use traffic counts, travel speed. As you can, this is a Columbus network, Ohio network. All the dots or the roads, the segment, all the road segment that we have the travel speed data from INRIX. All the dots here is counts every 5 minutes by car and by trucks. On top of it, we also have the public transportation, the APC AVL data. That means the passenger count at every bus stop for every bus run. We also know the bus vehicle locational, meaning every single bus stop when the bus vehicle arrives and when they leave. These are all high dimensional spatial temporal dimension data. We all throw it into this whole neural network computation graph and neural design. This will give you some idea what the scope of the research is. 5-second resolution. We have look at the 138,000 OD pairs and the network size is about 26. It's not huge. Right now we are running Southern California network, which is about 180,000 row segments, 16 million OD pairs. But this is kind of the pretty sizable. With this design on a regular computer, we're able to finish about 20 minutes or so. But here is the calibration results. Because with all the part of this whole framework, it might work better than the traditional approach. Is that now everything can be standardized, and you can throw into PyTorch and or TensorFlow, sort of a standard package. There's a very good, efficient, computation efficient way to calculate the gradient. So then everything can be moved very, very efficiently as long as you can come up with the best way to calculate the gradient. I know this is a whole different discussion. Itself is may want a whole lot of research. But again, just want to show you this. Every single dot means that it's a either 15 minutes traffic count at any road segment by car, by truck, and the same thing applies to the speed data as well. In general, you can see the calibration is kind of replicating what the actual road and transit system look like in Columbus area region. The one question, this was a project funded by the Honda R&D, and then at the time that we tried to throw out the what if scenario question, hey, what if we build some mobility service to connect people to fulfill their first mile, last mile services, connecting people to some of the major hubs in the area, right? So if that's the case with the mobility services, what type of changes are we going to see? So again, that's just based on the machine learning, the neural design model computation graph approach. Where we learned all the parameters, and on top of it, we just try to create a new. It's almost like think about the high dimensional space. So you try to with some physics model, then you try to extrapolate the results by saying, now if I have new additional service, here's what we see now. The bus ridership, bus market share can increase by 13%. Emission, VMT emissions, CO2 emissions can be reduced by 3 to 5%. So this is another follow-up work I have about 5 more minutes. So I want to quickly give a couple of more quick extensions, how would this whole framework entails. So this is another extension we did based on everything we discussed, kind of general concept, is now we can, but if you look at this framework, there's some issues. For example, one of the biggest issue is that when you go forward, right, this is called forward calculation, the whole process itself looks like in your design, it's this one off run, but actually because itself is a fixed point problem. So that has to go multi iterations and then that does not necessarily converge. So can we design a one single layer encoder decoder problem uh, with pure one layer neural network design? So that makes everything so efficient. Is that even possible? And that might be equivalent to the bi-level optimization model where you try to turn it to some kind of single level, but it's just that the way we solve the problem right now could be machine learning based. With that concept in mind, we kind of designed this whole approach, starting from the link flow from the very left. Link flow goes assuming some sort of separable link performance function BPR. Well, by the way, this is static. We still work on the dynamic case with this extension. But with the static setting, you can see from link flow to travel time, behavior model in the middle goes to softmax. Essentially, it's a logit model that gives you all the probability and multiply the instance matrix, goes to the link pass flow and again back to the link flow, right? So in the from end to end, this is a very close to analogous to machine learning world. This is encoder decoder problem. So it just becomes a single layer. Again, the best part of this is that you can add any loss function at any layer you like. If you measure the proportion p, for example, somehow it give you some, surveys or whatever. You don't know the count, but you know the p, so you can add some loss function there, right? If you measure the link flow, you only measure two links flow, and then you can add the loss function. So my point being that you can add any layer, you can design the loss function the way you calculate loss as you like, including this equilibrium loss. Essentially, is we want to minimize the gap from input and output. So this is you can see the input flow, link flow, and output link flow. We want to minimize that gap. This is what we call equilibrium loss. With that in the whole in mind, and we can calibrate many different factors. This is another sizable network. It's not so too big, but it's a sizable in SR41 network in Fresno, California. Thousands of links, not too much, but we do get day-to-day data. We have 141 counts from PEMS, 2,000 links, 5-minute by car, by truck speeds, 18,000 OD pairs, time varying. Sorry, in this case, it's the static. And then we also collect every single TAZ, all the social demographics, because we believe people might make very different choices based on where they are, based on social demographics characteristics. And then we also collect all the crash data, because sometimes people making choices based on how risky the roads are, right? We don't know, but we can throw it into the machine for it to learn. And also we had the bus data as well, and how frequent the buses and things like that, with the hope that we can throw into a lot of different features. Then we can use the system level data to learn about it. So this is actually the outcome that actually pretty very interesting. I want you to look at the very last column on to your right. So this A means it's statistically significant. You can see not only we learned about the origin destination demand, um, but you can see that it actually we created ground truth and it's actually pretty close. We also be able to replicate um, the alpha beta, which is surprisingly close to what many decades ago we recommended being 1 to 4. We didn't give it any prior value, which is we want the machine to learn. It turns out to be very close to 1 to 4. You can see all the losses among travel time, links flow, equilibrium. By the way, this is day to day. It's not just a one single typical day kind of scenario. The loss is very small. What's more interesting is that at the individual level, across all the OD pairs, remember every single one is making different choices based on their income, based on their travel time, the number of bus stops and risks and everything. You can see pretty much everything is statistically significant. And also it makes sense that people making choices based on reliability, right? That, the standard deviation, the travel time is higher, then you're more, if it's higher, then you're more like, it's uncertain means that you're less likely to choose that mode choice, more choices. By the way, we didn't get any individual level data. Everything is learned from the system level data. Okay, so a little bit of summary of why are we doing a computational graph approach, because like I said, and it's a lot of packages out there. The way that we calculate the gradient is more efficient, and also a lot of parallel computing. We can accommodate any data. It's a lot of flexibility, and we can also separate the whole concept of training, testing, cross-validation. We can apply multi-day, multi-year data. A lot of advantages. Of course, there's a whole lot of challenges. Last few minutes, I want to present some case study. Again, we continue to unify the data sources and under this framework and try to extend the work. One example is curbside management. There's this company we collaborated with in automotive and try to, they build the cameras and look for a lot of streets, blocks. We are getting the pickup, drop off, vehicle duration, park. It doesn't have to be park, vehicle parking. It could be pickup, drop off, uh, you know, uh, duration and the truck and cars and all these information by different vehicle classes. And or pickup drop off, they know, because in the pickup drop off pattern is very different under the camera. So we have that information at the street block level, and then let's see if we can add this data into the whole framework and to estimate, to calibrate the entire network. Again, this is a very similar computational graph approach. The only part is that now at the very bottom we add observe the curve events. You just have to build the right neurons in this whole layer, link follow layer, and then calculate the loss for those specific designated neurons. And compared with the actual data, again, the data itself is multi-dimension. Calculate discrepancy and use this forward flow and forward pass and backward pass to calibrate all the parameters based on the loss, right? So this is, and then we can apply that to what if scenarios. We actually here we have the multi-class count, multi-class speed for all the row segments, and also for some of the curb locations, and where we have the curb cameras, we also incorporate that. You can see the calibration, it works pretty well. Not perfect, but some are links are worse than the truck. Typically fits worse than cars. But we are able to replicate roughly the pattern of a pickup drop-off on top of all the traffic flow congestion pattern in the city level. So the other example that we did most recently is we try to leverage the satellite image data. The good part of the satellite image is right now it's relatively inexpensive. It also covers pretty much every single part of the city, because from up and bird view of the entire city, right? So unless there's the places where interchange has the blocking the view of the road underneath it, but in most of the cases, you should be able to see clearly that, hey, how many streets, how many cars on the street, and this is what we call typically it's called density information. Historically we have the traffic counts, we have the speed, but we never had the luxury to have the density data. And we're just thinking, hey, given the very ubiquitous density data, although it's very, very infrequent. So depending on how much budget you have, but for anything like a Google Street View free version, close to free version, the satellite comes every 3 weeks, and so you don't really get the real time. But I think that's for planning purposes, that's more than enough, right? All we need is that the citywide, every single street, we know the number of cars, number of trucks at the specific moment when the satellite took that image, and we can enter that piece of information to the model. Again, this is the same process. On top of the counts and speed data, we try to add additional kind of density data information into that whole process. The same neural network design, which is add one more loss function as part of the loss function term. And then you can see here, just in some examples, we can incorporate the parked vehicle. Nothing's perfect, but at least we can, on the images, we can extract all the vehicles and by cars and by trucks and parked vehicles, enter a framework. And this is just give a little bit of a way of seeing the density information across all the streets. And this is the Pittsburgh, down right in the middle is Pittsburgh downtown. This is the kind of Pittsburgh area. The calibration works pretty well in general, right? I promise this is my last slide. But in general, I think the takeaway here is that we try to come up with a way. We don't have the foundational model. It's something, some goal that we try to shoot for. The idea is try to come up with different geometry, different supply, different demand across different city, different people's perspectives and different behavior. Somehow, if we can design a very good embedding input space, maybe we can use the data to train the foundational model and then can be tuned, fine-tuned in certain places whenever you want to use it. But we're not there yet. But as part of this whole process, can we design a unified a computational graph approach where anything can be mapped into this whole different layers, and then you can adapt to any sorts of multi-source, multi-dimensional data to fit the model in a more automated way. That help us to calibrate network, replicate the actual system performance, and then we can create all, because everything is built on based some sort of physics model, traffic flow model. When I say physics, sorry, it's a metaphor, meaning that we actually use the way how people make choices, discrete charge model, and also we try to use the traffic flow model that governs how the vehicles move at the mesoscopic level. And then that will be a much better than a pure data-driven approach. Yeah, but we can also take advantage of other state-of-art machine learning approach, likely to be a better calibration. We're hoping the results, whatever they were predicting, the ability to predict will be more accurate than before. Okay, so that's all I have today. I hope time's still okay. But you know, this is not possible without all the funding agencies and the whole entire group. Thank you. I'd be happy to take any questions.
Thank you, Professor, for the presentation. We will be taking questions from the room. Yes, Professor.
Thank you, Mr. Qian. Very nice presentation. This was very interesting.
Sorry, I cannot hear you.
Yeah.
Maybe you can repeat my question. I should do it that way.
Yes.
That works too. Thank you, Professor Qian. Very nice work. I really enjoyed watching your presentation. And my question was about, you mentioned the different types of loss functions you can add to your model. I think you mentioned very briefly, but I wonder if you have any more information about this or expanded on this, because I was thinking about the types of data where there is a lot of data available, even in maybe smaller cities or cities that don't have a lot of attention. Have you considered using infrastructure condition data and looked at how much effect that has on the choices that users make?
That's a very good point. Very insightful. Thank you. Can you guys hear me? Yes.
Yes.
Yes or no? Yes, I think this is a great, very good extension of this work. And no, we haven't really considered the infrastructure condition. Maybe you, for example, you might be referring to some sort of a payment condition, and that's I think that's very relevant. I think maybe just thinking about this this particular case study. Right now, everything is based on the demand side, but certainly if you have the link level, pavement deterioration level or whatever, that information, yeah, so you can throw in there. It's more on how you would incorporate that into your decision-making process, and that term can be parameterized. So you can learn about the parameter rather than building this into the loss function, because I think all the loss right now is more on the demand side. I haven't really thought about how we can incorporate the supply loss, because the supply side right now, like I said, I'm assuming everything is fixed. When you learn this model, everything is fixed. But that certainly can change. And especially if you have, I was thinking if you have spatial temporal, like all the row segments, how they change over time, year by year. If you have like 10 years of data, yes, I think that, well, for sure you can throw into the demand side and how people making choices different way from year to year. Yes, but then you can also kind of throw out spend on the supply side being the output, and you try to reduce that loss. Naming everything can be endogenous. Yes, I agree. So that's a great thought.
Thank you. We have one more question.
Thank you, Sean. Thank you for the very nice presentation. Quick question regarding the you mentioned about the discrete equilibrium. Some of the decision layers you have are built upon equilibrium models, and then what type of a disequilibrium approach you have been trying? I'm just curious. This is very interesting. Second is that I have another question regarding transferability. I assume that most of the testings you have done are within the same network, right? I was thinking, have you tried to say some similar cities but different network topology, something limited difference? Have you tested whether your model can be used to explain a slightly different setting? Thank you.
Yanfeng, thank you. I didn't know you were sitting there. Hi, from modeling. It's good to see you. To your second question first, I think that's probably easier. Yes, well, I mean, our resources are very limited, but we try as much as we can to use this in many different cities. So far we have built Pittsburgh, Philly, Washington, D.C., Southern California, Columbus. These are the big original, and we took their MPO model, which is very large scale, and tried to calibrate it. We do work on some smaller networks as well, some municipalities, and for example, the SR41 network in California. I think I want to be very honest that there are cases that the goodness of fit is relatively poor. But I think that we look into more details. There's a lot of other issues had to be addressed. For example, data quality, things like that. But in general, I think it's at least it's feasible to run everything based on this framework. You just have to be a little bit careful, kind of for different cities, you have different set of data, the different quality. Then when the way you design this neural network, the computational graph approach in being more general, more specifically means that how do you design the neurons and connecting, building the behavior models might be slightly different. But my quick comments is that I think it's generally should be unifiable. To your first question, the equilibrium model, I think it depends on how you define equilibrium. I think even in the research community, we talk about predictive equilibrium, Boston. There are different ways of thinking about equilibrium. And also, there's a static and there's a stochastic, there's a dynamic, right? In this particular graph, I'm showing you, is this a static? And this is a very traditional, the very traditional route choice, stochastic. I mean, you can build a stochastic, or you don't have to. I mean, right now, in this particular graph, we use a stochastic. You can see some softmax here. That's a stochastic user equilibrium we build in. But again, so depending on how to define, you can just tweak this neuron design a very different way. In the dynamic case, we find that equilibrium, because again, if you have to run everything based on predictive user equilibrium for the dynamic case itself, it's a very big challenge. Like forward propagation, you really do have to do a lot of iterations. That we all know there's some issues about this dynamic equilibrium in the very large scale networks. And we do come up with another approach. It's somewhere between, there's a little, this is more of a kind of practical tweak. And then we, instead of running everything iteratively, then we try to do things based on some sort of a hybrid routing. It's somewhere between the UE dynamic user predictive user equilibrium versus the static instantaneous equilibrium. But then that way you can get rid of all this. But again, we probably don't know whether or not the true equilibrium exists. It really depends on your definition. Therefore, boiling down to this specific design is really up to user's choice, and you want to design whichever way you like to reduce that equilibrium loss. And you can design it in a very different spatial temporal dimension, as long as you can write out this loss function based on your neural design.
Thank you, Professor. Actually, we're out of time. Thank you, Professor Qian, for the great presentation. Everyone, please join me in welcoming Professor.
Thank you.
Thank you.